So far in our discussions, we've only spoken about frictionless systems. And so we saw how we only had a cosine function and the oscillations just continued to go. There was no change in them. But now we need to look at what happens when we add friction. So friction in our work with oscillating systems is a function of velocity. And if you don't believe me, take and rub your hands together slowly and then rub your hands together quickly. Tell me which one heats your hands up faster. Or if you don't want to do your hands, put some sandpaper to wood. If you move the sandpaper pretty slowly, it's not going to get warm too fast. But if you really start pushing and moving it quickly, the sandpaper will heat up. So the force due to damping is equal to negative b, some friction constant, times the velocity. And we can now add that into our formulas. We have mass times acceleration, function of t, is equal to, and now we have our friction force and Hooke's law. And put it into a standard form, that gives us mass times the second derivative for the distance, plus our friction coefficient. Velocity is the first derivative of our distance, and we've seen differential formulas like this that are very easy to solve. It's a homogeneous equation. So we take and come up with some test and put that into our formula. And we had actually used the coefficient on the highest order as being 1, so we can do that while we're putting it here. So we have the second derivative times a, or with a e to the rt, plus b over m, first derivative, a e to the rt, plus our k of the spring over the mass, and need the ae to the rt, do our derivatives, the a's will cancel, the ERTs will cancel, and I'm left with the formula r squared plus b over m times r plus k of the spring over m equals 0. And this is just a quadratic equation that we can solve with the quadratic formula. And we have the negative b over m plus or minus the square root of b over m squared minus 4. A is just 1, so we have k of the spring divided by m all over 2. Well, let's separate this out a little bit. And I'm going to distribute this 2 into each of these parts here. So I'm going to have minus b over 2m plus or minus 1/2 square root b over m squared minus 4 k of the spring over m. And let's bring this 1/2 inside. And if I bring the half into the square root, I need to square it, so that will be 1/4. Oh, this should be squared, sorry. So it'd be b over m squared minus 4 k of the spring over m. And I distribute through the 1/4. That gives me b squared over 4m squared minus k of the spring over the mass. So now we have the solutions. The question is, what do these solutions tell us? So the next section will be the different categories of damping.